Okay, this is the third hour for Physics 1C. We're going to be talking about this problem right here. Do you guys have any questions about anything? Everyone's still here? Okay. So this is the problem we're going to talk about now. I don't know how long this one will take. It's kind of complicated. But what we have here is a yo-yo shaped object with a mass of 5 kilograms and a radius little r. That's this radius here. I don't know if you can read that. That's little r. The inner radius is little r. And the b is the outer radius here. And then it has something called a radius of gyration. I'm going to talk about what this means here in a second, of 0.2. Has a chord wrapped around the central axis. This chord passes over a perfect pulley, that's here, and it's attached to a 2 kilogram mass. The yo-yo rests on a surface with a coefficient of static friction of 1.5. We want to find the acceleration of the center of mass of each object, this one and this one, and the tension on the chord. Alright? Radius of gyration is something where it's another way to define mode of inertia. The way that the mode of inertia of this object is going to be found is by taking the mass of our object, which is big M, and multiplying by that quantity k, the radius of gyration. This isn't something that's explicitly discussed in your book, but you know, it's like the mr squared, but it's just mk squared in this case. That's going to be our moment of inertia in this problem. So we've got an object. We can see what its mass. I'm going to write down all this information so it's easier to see. So the mass is 5 kilograms. The radius little r is 0.1 meters. The big radius we're calling b is 0.4 meters. And there's k. That's all we really need. The mass here, we'll call that be little m, is 2 kilograms. Okay. So we've got our object. I'm gonna do a circle inside of a circle here. We're gonna use this as a way to draw the forces acting on our object. Okay. Little r and b are the sizes of our object here. And this object has a chord that's attached right here. And I'm going to say that the tension in this chord, for example, at like the bottom down here, I'm going to say the tension in the chord here we're going to define as T. Because the pulley's massless, that same tension is going to be in this chord here, T. Okay. So let's now go and label all the forces that are acting on this yo-yo object here. Okay? So one of them is that tension T, which points straight to the right. What other forces is this object going to feel? And I should also probably identify that there's a surface down here that it's rolling on. What other forces does the spool feel? Normal and mg, right? And the normal force should basically be coming out from here, right? Its weight would come from the center. And then friction, right? One other thing to figure out here is, based on the way the spool's designed, which way is the object actually going to roll? Roll to the left? Counterclockwise, maybe? Counterclockwise would be like that, right? It's either clockwise or counterclockwise, I think you guys would agree. we can see the direction of the acceleration of the center of mass. And what I would say is that, God, I wish I could show you guys the demo for this. We have a demo at the school for this. It's basically either going to rotate to the right or the left. Let's see if we can do some calculations to figure out which way that the thing actually rotates. So, what is it that's actually causing this object to move? Well, it's because you've got this weight down here, right? And it's going to have its own little mg and attention. And if we solve for this object, we're going to say net force acting should be equal to the mass little m times what we're calling a1 right here, but I'm just going to call that a. The two forces would be little mg minus t, and those would be equal to ma. That's a very simple analysis that we can do for that one. For our spool, we're going to have three equations. We're going to have net force acting in the x direction should be equal to the mass of the object times its acceleration of the center of mass. The mass of this object is capital M. We're going to have net force in the y direction equal to 0. This is with taking x and y, kind of the normal directions, so to speak. And we're also going to have net torque equal to I alpha. Those are the three equations we're going to use to identify what's happening in this problem. Alright? So let's solve them all out here. For this one, we're going to get T minus F is equal to MACM. For this equation, we'll get N. I'll just skip a step and say it's basically going to tell us that capital N is equal to the mass of the object times gravity. Now, this one's a little trickier. We don't immediately know which way it's rotating. Okay, it could either rotate this way or it can rotate this way. We don't know what direction that is that it's rotating, and we also really don't know what direction it has. That's also going to be the direction of its angular acceleration. It's either rotating to the right or it's rotating to the left. So let's see if we can figure out why that would be the case. So if we look at our torque equation here, right, and we pick an axis for it to roll around, I would say the most natural axis for the rolling point would be the center of the object right here. That would be our rotational axis. If we choose that point, the normal force exerts no torque, and mg exerts no torque, right? Let's suppose for a second that it actually rotates in this direction here. And let's see what we would get. I would have a torque due to F, right, that would cause the object to roll in that same direction. That torque would be F multiplied by this distance from here to here, which is B, minus the torque due to the tension would be T times little r, and that should be equal to I alpha. Okay? Now we can do a few more things here. From this equation we see friction show up, and from this equation we see T show up. This equation tells us that if I take little m times g minus a, that's equal to the tension force. That allows us to plug this into this equation here. So we get little m times g minus a minus the friction force equals m. And I'm just going to say that this symbol a is also the same thing as ACM, because the acceleration of the center of mass of my object here, is it the same? Ooh, for a second there, I'm not sure. I think these are going to have some kind of ratio, actually. Because this object is not attached to the center here. Like, this thing is not attached to the center. But we will be able to make another statement here. I gotta stop back a second and think about this. I think I made a mistake here. I don't think I can say that. And I don't think we can do the step that we just did here either, now that I think about it. What we will have to say is that whatever ACM is, we know that it's going to be equal to r times alpha, where alpha is going to be defined using Um, which radius now? Would it be this one? Or would it be this one? Which one is it? What do you guys think? Which one of these should be the acceleration of the center of mass? Should it be r alpha or should it be b times alpha? You think it's big R? Oh, little r. So r is the little one, right? I think this is correct. I just need to think for just a second, though. I'm just going to scroll back to what I said at the very beginning of class. I've now completely confused myself, which probably doesn't help for you guys. If we go back to the very beginning of, not this, the rolling without slipping. Here. This radius is the radius of the whole object. And that's required so that it can roll through one revolution. It's the radius of the whole object. But in the problem we're doing down here, the radius of the whole object is b, right? Yeah, the string is the spool around little r. You're right. That's exactly right. The string is around this piece, where it's around this piece here. So I would say that the rate at which the string moves, right? Look. The rate at which... We're going to have to make some more space here. The rate at which the string moves is speed a. Would you guys agree? Or acceleration a. Where a1 is basically the acceleration of my block here. I think you guys would agree with that, right? But this acceleration, a1, this, I think, should be equal to little r times the angular speed. While I think ACM should be equal to b times alpha. So I think this is the correct one here. And we can relate these two to each other, right? Does that make sense to you guys? Or does that feel right to you guys? The string moves with acceleration a that's related to the rate at which this object moves down, which is called a1 in the problem. I think that's what we got to do. And then put everything together with our equations up here. Let's give that a shot. If I look at these two equations right here, this tells me we will eventually need to use the alpha equations. But if I were to divide these two, I would get that A1 divided by ACM is equal to R over B. Which then means that I can relate ACM and A1 together using this equation. Now I can take this guy, plug it into here. So we're going to get... I don't think we're ever going to use this equation. You might, though. T is m times g minus a1 minus the friction force is equal to MACM. Let's get everything in terms of the same variable. So let's replace a1. No, just a little room to write this stuff. Here it says that a1 is equal to ACM times r over b. Little r divided by b. This is actually a number, right? Little r over b is like, it's like 1 over 4, right? So we take that and plug it in here. So we have mg minus ma1 minus, let's move this to the left-hand side, m times ACM, and now we're talking about big M for the spool. That should all be equal to the friction force. We put all this stuff together where I have little mg minus ma1 is equal to ACM over 4 minus big M ACM. And I think this whole thing is going to become a number multiplied by ACM. So we're going to have, not entirely actually, is it? It's going to be mg minus, what, 5 over 4. Oh no, one is little m and one's... So it's really just ACM multiplied by M over 4. That looks bad. M over 4 plus big M. This algebra is going to get really messy now. So we've got that equation. We're going to make some space here, and we're going to re-solve these. Wait, what did I just do? Okay. No, I want to. So we've got this equation here. Why is it not pasting it? So copy, paste. It's because I deselected. We've got that equation. We've got our torque equation. I see what's happening. It wants me to paste it there. It doesn't want me to... Okay. No, stop it. Stop it. Okay. Do this here. And then move it over here. We got to put those two equations together. And we're also going to have to use some of our other relationships. So those are the two equations we need to push together now. Okay, so ultimately we're looking for acceleration right here. We're finding the acceleration of the object and the tension on the cord. We've already eliminated acceleration. The other equation we have was that alpha here and ACM are related in the sense that alpha is equal to ACM divided by B. Put all those three equations together, and we're going to get something like this. So F times B is going to be mg minus ACM times little m over 4 plus big M times B minus. The tension T was this, which means we're going to have to resubstitute again, which is going to be a little bit of work. So the tension T is M times G minus A1 was ACM over 4 right here. That's that equation there. So this is ACM over 4. I'm basically replacing T now with that equation there. Times R. Okay, so I've replaced F here, and I've replaced T right there. Hope you guys can see that. Equal to I. We said I was equal to this thing M times K squared, where K was this. It's not little m, it's big M. So it's big M times K squared, where K was equal to, I think, 0.2. Put that in here. Big M times K squared. We're going to start plugging in a lot of numbers here pretty soon. And then alpha gets replaced with ACM divided by B. And I'm pretty sure we have every single variable in this problem. We have a number for it, except for ACM. I'm just going to stop for a second. I know that's a lot of algebra. It's a tricky problem. Yeah. You guys lost? You guys have any questions? Alright. Probably a good idea. Start plugging numbers in here. Maybe. Let's try this. Let's take every term that has ACM in it and let's move it to the right-hand side. Let's multiply this out. mg times b. Oh, there's a question there. Please ask your question so I can help you out. And if you do see an error, please tell me. We don't know yet. we still don't know, actually. I guess I can make an argument as to why it's the case first. The force, the friction force F here, right? We know that it's less than the tension force, right? We know the friction force is less than the tension force, because it needs to move to the right. Because if this goes down, then this object needs to move to the right. Right? Like, if this goes down... So, what I would argue is that the friction force here is a distance 4 times as far away from the center of motion, or rotation, than the tension force. So since the friction force is 4 times as far away as this one, even if the tension's bigger, it would have to be 4 times as big in order for the object to rotate to the left. I think the friction's going to overcome, and it's going to rotate in this direction here, and not in this direction here. I think alpha is in this direction. And that's how I set up this equation here, was to put alpha in that direction. If this ends up leading to some kind of contradiction, like if we get a negative acceleration, then we're wrong. Okay? So what I'm doing now with our equation is to say that if I take mg and I multiply by b, I'm getting another term that's going to be this ACM times m over 4 times m times b, but it's going to have a negative sign, and I'm adding it to the right-hand side right here. That's that term right there. Then I've got to get another term here that's little mg times r, so minus little mg times r. Right? And then I have a term that's going to be, well, this is a negative here. So that's going to be, here, another term that's going to be like plus m times g plus m, oops. I already put that term in there, right? mgr is the first term here. There's another term that's going to be m times acm divided by 4 times little r. And then this we're going to subtract to the right, and we're going to put it inside of here. So it's going to be little m times r divided by 4. That bothers me, that negative sign right there. Make sure we did that right. It was FB minus TR. The T was G minus A. The negative A came from this equation. That looks right. No, this feels correct to me. So ACM is multiplied by mk squared over b right there. It's also multiplied by mb, and it's also multiplied by mr over 4. And that's this term here. So now we can, I've already moved that term to the right-hand side, so we can get rid of that one. This is our whole equation now. mgb minus mgr is equal to all that junk right there, which can turn into a number. So let's remember what our values were here. Let's take our values here. God, I hate the way that there's this delay when I do that. Whatever. Copy. Paste. So what do we got? Do you guys care if I just don't put units in? 5 times k. K was 0.2. B was 0.4. Plus little m over 4 would be 2 over 4 plus big M, which is 5, times B, which is 0.4, minus little m is 2, times little r is 0.1. Ooh, that looks bad. K is squared. Thank you, sir. Appreciate that. K is squared. Okay. So it's 2 times little r is 0.1 divided by, this is multiplication here, divided by 4. So little m was 2, little r is this. We put big M in this term right here. The left-hand side is mgb minus mgr, so that's basically just mg times b minus r, which is going to be m, which is 2, times g, which is 9.8. Now this is the one thing that's not going to cancel out of everything, and then times b minus r. Well, b minus r would be 0.3, right? All the other units should cancel. So we get... You guys can calculate this if you want to. The right-hand side, what I got was 2.65 ACM. And the left-hand side, you're obviously going to get, like, what, point? Well. So this is going to be 0.06. Did you calculate that right? No, I did division. Okay. Sorry, that's wrong. 2 times 9.8 times 0.3. 5.88. So I think we're going to get ACM is equal to that divided by 2.65. So about 2.21. And there we go. It would be important now to prove that these things are actually true, right? That this, no, that's not exactly the right way to say it, that this term is actually greater than this term. Would be worth proving. The other part of the problem was to solve for tension, and to solve for tension we can use that equation right there. Or really notice here that this was really what the tension was. It's basically mg times ACM over 4. So if we do that for the solving for the tension, we would get T is equal to m times g minus ACM over 4. So the tension T is going to be equal to the mass. Little m was 2 kilograms times 9.8 minus 2.2 divided by 4. And Jesus, this problem is so long. So this is 9.8 minus 2.2 divided by 4 times 2. You get 18.5 newtons. And if we wanted to solve for the friction force, I guess we would use that equation. We're getting a little delay here. I don't know if this file's getting too big or not. And yeah, we could use this equation here to solve for the friction, right? Which actually shows up again right there. Let's leave that on the screen. So if we do that, so that's our friction force. Then we can solve this one. So 2 times 2 kilograms times 9.8 meters per second squared minus ACM, which was 2.2, multiplied by little m over 4, so that's 2 kilograms divided by 4, plus big M, I think was 5. Yep. So we end up getting that the friction force is equal to, you get 5.88? Is that what I'm about to, oh, 5.88 was from something else, wasn't it? Yeah, on the left-hand side? Okay. So now it's 2 times 9.8 minus 2.2 times 5.5. And this is 7.5. But then to figure out, like, which way it rolls, it was like this F times B minus T times R, keeping in mind that R is 0.1 and B is 0.2, the friction force would need to be 1/4 of this in order for it to roll the other way. So there we go. Negative 7.2? Did I make a mistake? Oh, okay. Yeah, it does roll clockwise, which if you think of what that means, let's go look at the problem. I'm reasonably certain that if you try it with the other assumption, that you'll get some error somewhere along the way. Like, reverse these, assuming that it rotates the other direction, and you're going to get some kind of a negative something somewhere, like a negative force or something, or a negative acceleration somewhere that won't make any sense. What does this thing do then? If it actually rolls to the right, okay, that means it basically, it winds up as it rolls. You know what I mean? Like, the spool, right, is going to wind up in this direction, So it's going to be rolling. It's going to kind of like, you see what it's doing? It's like rolling up itself instead of unrolling itself, right? You take a yo-yo and you hold it straight up and down, right? You put your fingers through the ring or whatever, and then like you let the yo-yo descend. It unrolls itself, right? Same thing would happen if you take a roll of paper towels and you hold one of the paper towels and you just hold it up and let it go. It would unroll itself, right? But this thing actually rolls onto itself as it moves due to that friction force here having a larger, you know, moment arm than the tension force, which is going back this way. So the friction force wins in terms of torque, and it makes the object roll up as it rolls. I really wish I could show you guys this. It's very surprising to watch. Like, it looks weird when you see this. That is correct. It is possible that if the numbers change in the problem, it might actually roll the other direction. And if the, let's say, like, if the inner radius here was a little bigger, right? If the inner radius that it was moving on here was, like, let's say, quite a bit bigger here, then it may actually roll the other direction. Yeah. Okay, so that's what I would say is a very challenging problem regarding... This takes everything into account we've learned so far in this chapter. It includes the relationship between torque and angular acceleration. It includes moments of inertia, and it also includes rolling without friction, because we had to employ some standards. And then you notice also that one of the really tricky things here is that the acceleration of the center of mass of this object is not the same as the acceleration of this object, and you need to have these two relationships, this one here, and then eventually this one here. Sorry, what was it? This one, A1 equal to R alpha. Why can't I just get the little selection tool? I've got selection tools left. What chapter from the text are we doing right now? Currently, this is from chapter 10 or 11. I'd have to pull the textbook up to check for sure. 10 or 11. I get it mixed up because I'm using two different textbooks. In your textbook, the chapter that we're doing right now is these two chapters. This is where we are, 9 and 10. We're kind of in between both of them. Next time, what we're going to be talking about, see, this is like torque and angular acceleration, rigid body. What we're going to be moving on to next is tempo. Really, it's mostly chapter 10 this stuff shows into. I'll show you like some of the problems that we did. This is kind of like what we just did a couple days ago. Here's the rolling without slipping condition that we talked about today. Race of the rolling bottoms, this was a problem that we did today. And then here's a yo-yo, kind of like what we just did, except for more complicated. Here's the acceleration of a rolling sphere. We did this for a rolling disc. And what we're doing next is, this is the next, like, basically the entirety of next week will be devoted to angular momentum. That's our next topic. Okay, so we're basically in chapter 9 and 10 here. There's topics from both of these that kind of overlap, but they split them up into two. Oh no, I lost my, there's that, and then there's that. Does it conclude what you need for homework 10 on mastering physics? I would have to look, but I believe it does. I'm pretty sure that it does. Let me go ahead and just stop the recording now.